welcome everyone to the first plenary lecture of this year's series of Young Mathematicians Conference. Hope you've been enjoying so far your talks by your peers. Now we're going to hear about resolution of singularities by Karen Smith. So Karen is one of my personal heroes. She works on beautiful algebraic structures, and her research mainly lies at the interface of commutative algebra and algebraic geometry. Her work on tight closures has been celebrated and been very, very inspiring and actually groundbreaking. She did her PhD in University of Michigan, where she is actually a professor now. Her advisor was Mel Foxter. She held positions at Purdue and MIT before going back. She is a very, very enthusiastic mentor of both undergraduate and graduate students. She has advised about 18 PhD theses according to the mass genealogy. She's been a speaker at the ICM in 2014. She's received numerous prizes, including the Satter Prize in 2001. She was another lecturer at the joint meetings in 2016. She's a fellow of the AMS. She was a Sloan Fellow, NSF Fellow, multiple honors. Okay, well, without further ado, let's hear from Karen.
So thank you and welcome. Thanks to everybody for coming. I want to tell you a little bit about my area of math. I'll mention a theorem I proved, actually two, but it's going to be pretty light on the technical details because it's a broad audience and it's a young audience. These are some of my favorite things to talk about, so I hope it'll be fun. So algebraic geometry is a branch of mathematics. It's actually one of the oldest branches of mathematics. And what it is it's the study of geometric shapes defined by polynomials. Or you can think of it as the study of solutions to polynomials. So this has been going on since the Greeks. I mean, it's been going on for a very long time. And you've been doing it since high school, because you know that y equals x squared is a parabola, and x squared plus y squared equals 1 is a circle of radius 1, and all these kind of things. And in fact, you've probably seen all of these things early in your math education. These are all examples of the things we study in algebraic geometry. Even this one, although it looks like it's defined with a sign, it's secretly a polynomial as well. It's secretly defined by a polynomial as well. So algebraic geometry is essentially the study of these things. But to be more precise, let me give you the precise definition of the objects we study in algebraic geometry. These are called algebraic varieties. So an algebraic variety is a geometric object. It happens to be a topological space, if you know what that means, but it doesn't really matter. It's a geometric thing. And I'm only going to be talking about affine algebraic varieties, so I'll just say variety. There are slight variations that you don't have to worry about. So a variety is always a subset of some complex n-dimensional space. And what it is it's just the common zero set of a bunch of polynomials. So if we're looking at subsets of Cn, we would be talking about polynomials in n variables and where they vanish. So for example, the parabola is the vanishing set of y minus x squared, right? I only drew the real points, and in high school we only drew the real points, but we could draw the complex points or imagine them at least. So here on the slide, there are 5 different pictures of algebraic varieties. So you can already see that there's a lot of variety among varieties and how they look. And these guys are almost the simplest things we could possibly write down. So already they look pretty complicated and interesting and different, but they are all of them given, except for this tan background one, which you can tell is not professionally produced. It's produced by me. The other ones are produced by my friend Herwig Hauser, who has this beautiful gallery of algebraic surfaces, all different kinds of varieties. So the 4 on the black background are all given by just one polynomial in 3 variables. And I've described the polynomials here. Does this have a pointer? Looks like it does. So for example, this blackboard bold V here means vanishing set. So this union of these 3 coordinate planes is the vanishing set of the polynomial x times y times z. If you think about where x times y times z vanishes, it vanishes if and only if x is 0, or y is 0, or z is 0, and those are the three planes where z is 0, x is 0, y is 0 here. So this is, extremely simple case of an algebraic variety, but it is an algebraic variety, and likewise, so are these guys. You can see that they're more complicated. All of these, however, even this Whitney umbrella here, are still about as simple as they can be, because look at how low the degrees of the polynomials are here, right? And again, these are just one polynomial zero set in three variables. So these are some examples. This one's a little different. It's also in C3, but of course I'm only drawing the real points. I'm drawing it as if it's in R3. And it's given by two polynomials. So this is the vanishing set where both xz and yz vanish. So how can you have a point where both xz and yz vanish? There's basically two ways. If z is 0, then both of these polynomials are 0, right? X times 0 is 0, y times 0 is 0. That's this z equals 0 plane, the xy plane in free space. But if z isn't 0, it's still possible for both of these things to vanish, right? That can happen if and only if both x and y have to be 0. So if both x and y are 0, z could be anything, and then every point on that axis, that's the z-axis there, x and y are 0, z is anything, they all satisfy both of those equations. So this variety is different than the other three because it is defined by two polynomials instead of just one polynomial. You might wonder, is maybe there one polynomial that defines it? It's a good exercise to think through. If we're thinking in R3, there is one, but if we're thinking in C3, it turns out there's not. Okay, so what other things can we notice about these varieties? Well, they're interesting. There's this cooling tower here. Notice it's smooth. And I'm not going to give you a precise definition of smoothness. You could actually probably define it yourselves if you've taken multivariable calculus and think about derivatives and stuff like that, maybe for when you have one equation. But anyway, it's smooth. If I pick a point on it, it kind of looks locally like a little patch of smooth, just ordinary R2. In this case, it's really C2 because, again, I'm only drawing the real points. So this is a smooth variety. None of these other guys are smooth, although they have smooth points on them. For example, any point here except the origin is a smooth point. And likewise here, we only have to avoid the axes in order to have a smooth point. Here, it's a little harder to see what's going on, but there's this axis here that's not smooth. Here, it's even harder to see what's going on. A little kind of pinching and curling going on. But in any case, I'm going to be talking about what it means, or just about the idea of smooth varieties being nicer. See, if you have a smooth variety, it turns out that it's a complex manifold. So I don't expect everybody knows what that means. But basically what it means is you have all the tools of complex analysis at your disposal to study it, and so it's a good thing to have a smooth variety. These guys are more complicated. Alrighty, so that's our definition, and I think I should say a couple of words about why am I doing C? Make it sound so complicated. I drew the pictures in R. We can only really see R anyway. Why am I doing C? The reason is that zeros of polynomials naturally lie in C. Right? If I take the polynomial x squared plus 1, are you going to tell me it has no zeros? Well, you could, but then you'd be missing part of the story, right? What it really has is two zeros, I and minus I. So the variety defined by this polynomial, x squared plus 1, that's not the empty set. It is the set plus or minus I, a set of 2 points. There are no real points in there, but that's the variety. So this is going to be true always, if we take, for example, x squared plus y squared equals 0, and look at what's that zero set of the polynomial x squared plus y squared inside of the real plane. The only way that can happen is that x and y are both 0, but inside of the complex plane, this is actually two lines crossing. And to see that it's two lines crossing, I factored the polynomial c. I can factor that polynomial if I allow complex numbers. And now the vanishing set of a product, just like we did before with x, y, z, is the union of the corresponding vanishing sets of each of the factors. So we get the two lines of slopes I minus I, whatever that means. I'm going by analogy with what you know from high school. So I'm not saying that the real points on a variety are uninteresting. Far from it. In fact, there are many mathematicians that study that subject, but they're not really algebraic geometers. It's a different flavor of mathematics. Likewise, many people are very interested in the rational points on varieties. That's a subject of mathematics called arithmetic geometry. And for example, you can see that if you think about Fermat's last theorem, we're interested in when this polynomial has no integer, whether or not it has integer solutions, other than the obvious ones, where one of the variables is 0. And so that's a question about the integers points that satisfy that, or you can divide denominators and say the rational points that lie on this complex variety. This, as a complex variety, is actually a two-dimensional thing in free space. And I should say a word about dimension, because going back here, let me go back to this previous slide. Sorry, this slide. So I call all of these things surfaces because they all are having complex dimension 2. The real points have real dimension 2, but if I really draw them in in C3, they would be 4-dimensional, right? Because each copy of C is R2. So whenever I say dimension, I'm talking about complex dimension. But don't let it bother you too much. Just follow along, because I think you can follow, even if you get confused about that. Okay, so everybody should know linear algebra. You probably can't get an REU unless you've studied linear algebra. And I want to point out that algebraic geometry is kind of a souped-up version of linear algebra. In linear algebra, one way to think of what we do in linear algebra is we study 0 sets of linear equations, systems of linear equations, right? So points and lines and planes and higher dimensional linear spaces, those are all special cases of algebraic varieties. In algebraic geometry, we study solutions of systems of polynomial equations. And of course, they're much more complicated. They're not just points, lines, planes, and so forth. So just like in linear algebra, you can do it over R in your first course in linear algebra, or you can do it over C or any field later when you take linear algebra. Same is true in algebraic geometry in the exact same way. Okay, so why study varieties? They're everywhere. Actually, I personally think they're just interesting, and that's the only reason I really study them. But they are actually everywhere. So, well, you've seen them in conic sections in high school, and then there's a long list of things here. Most of you guys don't know any of those other words. That's fine. I'm just trying to tell you, and you might know 1 or 2 of them. These are just some of the places in all different kinds of areas of mathematics where they come up. For example, a lot of times what happens is a mathematician wants to study the set of all objects of a certain type. So we might want to study the set of all. I was just in a talk. Is the person who gave the talk at 3? I don't remember. Somebody's talking about the set of all objects of a certain type, but I don't remember what the type was now. But for example, maybe we want to study the set of all compact Riemann surfaces. We want to study the set of all of those things. Maybe we fix them to have genus phi or whatever. So it turns out that that set of all those objects of a similar mathematical type form a variety. Or they might form a variety. Many sets of objects, classes of objects, form varieties. And this is why people in mathematics, all over mathematics, are interested in varieties. They just come up, even if you just want to study complex analysis, or if you just want to study number theory. They come up anyway. You're forced on you. Okay. So that's one of the reasons they come up everywhere. The other reason they come up everywhere is they're extremely useful in applications, because you can model incredibly complicated behavior with polynomials, or at least piecewise polynomials like in Toy Story. Those are piecewise algebraic varieties. Cut out little pieces of space where you have one variety for the arm, a different variety for the hair, or whatever. So they come up everywhere. Polynomials are, they both model complicated behavior, and they're easy for us to manipulate. The computer can manipulate them and multiply them and add them and do all kinds of stuff with them. So if we were trying to do this with a general continuous function, forget about it. Even a general analytic function or a general, smooth function, computer doesn't understand what that means. Polynomial, it understands. Okay. So there's lots of applications too. I tried to mention a few of them. Okay, but what kind of questions do algebraic geometers ask about algebraic varieties? And what I want to talk to you guys about today So the first thing you do in any sort of geometric subject or algebraic subject in mathematics is try to understand what are two of the kind of objects you're talking about the same, right? So you do this in group theory. You say, one of these groups isomorphic. How can I tell if two groups of the same order are isomorphic? And we do that in topology. We say, how can I tell if these two topological spaces are homeomorphic? And in algebraic geometry, we also ask that question, and we want to understand and have techniques at our disposal to tell if your variety who arises studying Riemann surfaces and your variety who arises studying vertex operator algebras might miraculously happen to be the same variety. You've just opened up an incredible field of new tools. Because if you're studying one kind of a parameter space, turns out to be the same as a totally different parameter space in a different type of mathematics, you can use tools in that other area now. Or more likely, you find somebody to collaborate and learn those tools from that. Collaborate out. So that's a critical question in any branch of mathematics, basically, or at least any sort of topological, geometric, or algebraic area of mathematics. I don't know if analysts really ask that question. They probably do too. I don't know. It turns out to be incredibly hard. First of all, maybe I should tell you what I mean by the same. So what I mean by the same when I'm talking about algebraic varieties, so here what I've tried to show you is a parabola. So that's the zero set of y minus x squared. And down here's another line, which I can think of if I want in two variables, the zero set of just y. That's where y is 0, the x-axis. These two varieties, the line and the parabola, are isomorphic algebraic varieties. They're the same algebraic variety up to isomorphism. And the reason is that there's a map that's given by polynomials in the coordinates that takes every point on this to a point here. And there's a map going from here back up to the parabola that takes every point to a point on here using polynomials in T as the coordinates, polynomial maps here. And not only that, but it's bijective. So it's a bijection which is given by polynomials in the coordinates. That's what we mean by isomorphic. You don't have to remember this. I'm just giving you the feeling of what algebraic geometry is. It turns out to be very hard to tell when varieties are isomorphic. For example, a huge open question is how can we tell when varieties are isomorphic to just Cn? Rational varieties is a very big open problem, even in 3 space and 4 space. 2 space, it's a little easier. So, and in 1 dimension, it's very easy. But so this is a hard question. So what do? You guys just did an RU. When the question's too hard, what do? Simplify it by asking an easier question. I was afraid you'd say, look it up on Wikipedia. I think you guys are past that. Yeah, you ask a simpler question. Or maybe you ask somebody for advice, but they'll tell you, ask an easier question. So what we do in algebraic geometry is instead of demanding two varieties be isomorphic, and people do study that, that's an important area, but another huge branch of algebraic geometry called birational algebraic geometry is understanding varieties up to almost everywhere isomorphism. So this little cusp thing here is not isomorphic to the line, as you can imagine, because it has a pointy thing on it. It's not smooth, and the line is smooth, right? However, if I remove that one point there, I can find polynomial maps going bijectively in between this line minus the origin and this curve minus its origin. Those are isomorphic to each other, except at that exceptional point we removed. So that's called a birationally equivalent, that this curve is birationally equivalent to that line, and that's what I mean by almost everywhere isomorphism. And the business of trying to classify all algebraic varieties up to almost everywhere isomorphism, you may have heard of it. It's called the minimal model program. Maybe you heard it somewhere. Some people call it the Mori program. So there's several fields metals embedded in this question. Actually, same is true here. But it's a difficult ongoing subject, recently solved in dimension 3, relatively recently. Anyway, so these are important questions. If we focus on one variety, just one variety, we can ask lots of questions about how it looks. So for example, maybe it came up in some study of something, maybe even studying DNA. I'm making this up. I don't know any applications of parameter spaces of DNA molecules, but it could happen. Who knows in 50 years? and you know that the object that you're studying is a variety, and you'd like to get your hands on it, but it's difficult. You don't know, for example, how many defining equations does it have? How many dimensions does it live in? As you see with this parabola, it lives in 2 space, but it's isomorphic to something that lives in 1 space. So if we can simplify our problem by embedding it as an isomorphic thing in a smaller space, that'd be a good thing, right? So an important question is, what is the smallest dimensional space into which your variety can be? So there's an isomorphic variety in that smaller dimensional space, in other words. And then, of course, you might also want to ask, if you're doing applications or really trying to use a computer to crunch around on it, is can you parameterize the points on the variety? You know, can you just somehow give a very simple way to explain what the points on the variety are? Obviously, I can parameterize this parabola, and in fact, I gave you a parameterization. This guy can also be parameterized. T goes to t squared t cubed, parameterization. But not every variety can be parameterized, that's the question. It's not that we don't know it. We know there are ones that cannot be parameterized. Okay. So these are just some background, general questions that are in the field. Almost these kind of things could be in any field that you study, in geometry, any class of objects. And now we get into more what I want to talk about in this talk, which is about smoothness and singularity of algebraic varieties. So, for example, we already identified that some kinds of varieties might be smooth, and that's a better thing, like this cylinder and this saddle are both smooth algebraic varieties, so they're going to be easier to work with. We're going to have differential forms on them and complex analysis and all kinds of nice stuff. But in general, if your variety came up in some context somewhere, you might not know that it's smooth, and you won't want to be able to identify whether or not it's smooth. Or you might want to say, well, it's not quite smooth, but gosh, it's a union of 3 smooth things in a simple way. Right? This guy is not smooth, but it is just a union of 3 simple smooth things, 3 planes. Right? So that's a resolution of the singularities, to think about that thing as really a union of 3 planes. Or, you know, this guy's not too bad either. It's got 1 singular point and that cone point. This guy's got 3. It looks a little bit more complicated, and this is a lot more complicated. So we'd like a way to understand how singular are these things. Can we actually measure how singular they are? And can we somehow find an approximating smooth variety? A variety which resolves the singularities. So like here, if I take these 3 planes, I can think of those as a resolution because I can map those to that configuration, actually using polynomials, and it'll be a nice map. And it'll be an isomorphism everywhere except where those crossings happen. So that guy is birationally, is almost everywhere isomorphic to 3 planes. Disjoint union of 3 planes, which is a smooth variety. So anyway, these are the questions that I want to ask. How can we tell if it's smooth? Can we get rid of singularities in some natural way? And then can we also quantify how bad the singularities are in some way? So let me tell you more precisely what I mean by a resolution of singularities. So you don't have to absorb what's up there. Most of it's details that don't matter that much. It does have a precise definition. What I want you to think of is that we have a variety, which is that V in that plane there. It's a simple variety. It's just defined by 1 equation and 2 variables. It makes like an alpha curve. I'm going to imagine it here on the floor, an alpha curve on the floor. And it's really easy to resolve its singularities, because what we can do is we can kind of imagine a little pole here poking down through the singular point and just kind of lift up that cone, lift up that curve, so that it comes in 3 space as a nice smooth curve like that. That's a resolution of the singularities of that curve. And in general, you can ask the question, given any variety, so like one of these guys, is there a similar kind of thing that can be done? Not at all obvious that there would be. Not at all obvious that there would be. Except for the first one, we discussed the way you might do that. So here's one example where it can be done, and this is from an RAU project. That's why I put this up here. So these students, Juliette Bruce, Molly Logue, and Robert Walker, studied the curve that's described up there. So it's actually, those are just 2 examples of the kinds of curves they studied. So these are just defined by 1 polynomial, very simple polynomial, and 2 variables. And they gave an algorithm for how to resolve its singularities. So I don't want to say that they were the first ones to show that these can be resolved. Curves we know, have theoretically resolved since, I would say, 1800s, but somebody would tell me, oh, Newton knew how to do it. Newton's not that. You know how people do that in math. You know. Yeah, I mean, Newton kind of did, but he didn't define it all the same way. But Riemann did know this kind of thing, how to resolve singularities in the sense of finding another curve that's smooth and mapping onto yours properly, nicely, and that it's an isomorphism except at the points that were singular. So these guys found a really nice algorithm. So you can't just kind of straighten this thing out because that's not given by a polynomial map. These have to be given by polynomial maps. And they have a really nice algorithm that's published in the Journal of Commutative Algebra. I think actually this might have been presented here, but maybe somebody else knows. That'll be a few years ago, though. Oh, maybe I should also tell you guys, these people have gone to graduate school. Juliet is a PhD student at Wisconsin, and she's working with, she's doing commutative algebra now, which is kind of a branch of algebraic geometry. And Molly got her master's from Wisconsin in math, and now she's working in computer science in Boulder, doing a lot of climbing, even though it's Juliet who's climbing here. And Robert's a PhD student in Michigan who's going to be graduating next year. All right. So here's the amazing theorem. This is my favorite theorem in mathematics. It's an unbelievable theorem. Every variety, every single zero set of polynomials I can write down. All those crazy pictures we saw. And way crazier, many more variables, way more complicated. Every variety admits a resolution of singularities. So in this picture, I have a nice variety. You guys can all tell me the equation. The zero set of the polynomial in three variables, right? Doesn't really matter too much, but it is a variety. And its resolution of singularities is this cone. And it's actually pretty easy to write down the map. I didn't write it here because it jumps up the slide and it's not that important. But maybe I'll tell you, if I take a point, so here I'm going to take this cylinder to be the in 3 space, x squared plus y squared equals 1. So the z isn't appearing in there. Z can be anything. That's because I'm going off. It's like the circles are all lined up along the z-axis. This is the cone x squared plus y squared plus equals z squared. That's what this is. X squared plus y squared equals z squared. Sorry, I got my z going horizontally. I know people don't do that in undergrad usually, but whatever. So then the map is x, y, z goes to x, y, and then, sorry, x, z, x, y, and z. Very simple map. That's a polynomial map of the coordinates. And what you see is this guy is smooth, and it's mapping bijectively onto this thing, except that that vertex point here, I need to remove it in order to make the map bijective, and I need to remove the pre-image of it, which is this waist around this cylinder here, that belt. I got to remove that. And if I do that, then this map is invertible. I can write the map going the other way. This is an almost everywhere isomorphism of this singular variety with this smooth variety. This is a resolution of singularities. And you can see it's kind of beautiful, actually, I think, because you might not have thought of that. Here I can prove this, by the way, for surfaces. Again, this is one polynomial in 3 variables. It's a 2-dimensional variety. For surfaces, this was actually known in the early 1900s. The Italian algebraic geometers could do this. But what Hironaka did is for any dimensional variety. So again, you got to imagine that the variety could be in 17 variables in 17 space. Maybe it's defined by 145 equations. Right? And maybe its dimension is 8. And its singular set might be 6-dimensional. And its singular set might be all curled up on top of these, it might have singularities too. By the way, singular set of variety is always a variety. They come up everywhere. You can't avoid it. Singular set of a variety is always a variety. So it could have singularities upon singularities upon singularities. So this is actually an incredible theorem, even in dimension 2. Actually, even in dimension 1, but it is pretty easy to do in dimension which I'm not going to do for you guys. But just repeating how amazing it is. You know, all of these guys have a smooth variety that looks almost like it almost everywhere. Every single one of these guys, there's some variety and there's some natural map given by polynomials, and actually, you can actually always make it be a projection. You know, x, y, z goes to x, y. To do that, though, you have to go into some very large dimensional space usually to make it a projection. But imagine, each one of these things is a projection of a smooth variety from a higher dimensional space. And if I cut out the singular points on those things, it'll be a bijection. If I cut out the singular points and the things above them, I'm actually. So it's really a remarkable theorem. Yeah. Anybody have any questions about it? Yes.
Is it like a branch cover kind of?
Usually when people talk about branch covers, they're talking about two things that are both smooth, one mapping to the other, and it has, you know, not necessarily one everywhere. But in the sense that a branch cover is going to be like n to 1 if you remove certain points. Yes, this is going to be an isomorphism if you remove certain points. In that sense, it's like a branch cover. Yeah. But it's 1 to 1, not n to 1. Okay, branch cover. Okay. Are there any other questions? Yes.
What's this mean in terms of the coordinate ring?
I'm getting to that. Yeah. I didn't define a coordinate ring yet. I meant to ask if there were any questions back here too, and I forgot. But maybe I'll keep going. You guys can also ask me afterward or dinner. Unless anybody has an urgent question. You can also interrupt me anytime. Don't be shy. All right. So where were we? So I wanted to move in. So I want you guys to appreciate this theorem. You know, that's the takeaway, that what the theorem is saying. The theorem, it's amazing. And it comes up all the time. This also comes up even in analysis. It helps some analysts solve their intervals converging or not things using this theorem. Really deep theorem. He got a Fields Medal for it. So you know it's a deep theorem. All right. So why do we care about the theorem? There's many reasons we care about it. One reason is that if a lot of times you can, if you know the variety that you want to or need to or are forced to study has singularities, you'd really like to not have to deal with those singularities. At least many people, I like the singularities. That's my specialty. A lot of people just don't want to deal with them. So they want to replace their variety by this smooth approximation, this resolution. And one of the things you need to understand, if you're going to do that, is really how complicated is the resolution? Like how much different is it than the thing you started with? So in the examples we saw so far, it wasn't very different. With that alpha curve, there were only sort of 2 points on the resolution that had to be removed. And in the cone for the resolution, there's just that one circle around the cone, the cylinder that needs to be removed, and the vertex in order to make it an isomorphism. Yes. Yes. Yep. In whatever sense you mean by measure, yes. It's a lower dimensional variety. It's a good question. It does. Yeah, so in order to tell how complicated is the resolution, which is a way of saying how complicated is the singularity, we define this thing called the exceptional set. Now the exceptional set is just a preimage of the singular set. So in the exceptional set of the cone is that curve, that circle on the cylinder, and the exceptional set of this alpha curve, or the resolution of the alpha curve, are the 2 points that map down where the alpha curve is created, where the branches cross. So part of what Hironaka proved is that exceptional set can always be taken to be nice. By the way, no one asked me if a resolution of singularities is unique. No. There can be many, many resolutions of singularities. They're not unique. And actually, a huge branch of very active algebraic geometry right now is trying to figure out what's the best resolution of singularities to take. It's called the canonical model. Canonical model. It's part of the middle model program. So we'd like to find sort of the bottom one, or the best one, or the most representative one. There can be many of them. But in any case, the exceptional set is that can be taken, part of what Hironaka proved is this exceptional set can be taken to be just a union of smooth varieties. It's kind of amazing. Just a union of smooth varieties. Here, it's on the cone, it's just the one curve. That's a smooth variety. The circle is a smooth variety. For the alpha curve, the exceptional set, for those 2 points, 2 distinct points, 2 disjoint points, that's also a smooth variety. But in general, even for this wacky thing here on the right, that also, I don't know what it is, but it has a resolution of singularities, and the preimage of that singular set is a union of smooth varieties. And they cross transversely, if you know what that means. They cross nicely, they're not tangent to each other. So you can imagine that thing must be pretty complicated, because in that picture there's the singular set's 4 different lines, and they're crossing each other as well. It's like folding away around itself in a weird way. Okay, so some of the things you might be interested in studying if you want to understand how singular is your variety, how far is it from being smooth, you might want to understand how bad is the exceptional set. So you might ask lots of questions depending on your field of math. You know, if you're a combinatorialist, maybe you just count how many components there are. What's the minimum number of components? Or if you're a topologist, maybe you ask, what is their homology? Or if you're in algebraic geometry, you might be forced to deal with both of those things. There's all different measurements we can put on them, and that's part of what I want to tell you about. So Mike Arkin was one of my mathematical heroes. He was my postdoc mentor at MIT a long time ago. He identified a class of varieties that are almost smooth called rational singularities. So when I say almost smooth, what I mean is if you take the variety and then you find a resolution of singularities and you want to do some mathematics on your variety, like compute an integral or something like that, you can do it on the smooth thing. So it's close enough to the smooth thing that no terrible thing goes wrong, and you can just blindly replace your singular variety by its resolution and proceed. So if you're happy that you have a smooth thing to deal with, you're going to love rational singularities. And mathematicians do love rational singularities. It's a question that comes up all the time about does this variety have rational singularities? So here I tried to explain a little bit about what his definition is. It basically just says that the exceptional set is relatively nice. It's for a surface. I'm lying a little bit, but I'm trying to keep it accessible. Basically just means that the singular set is a union of Riemann spheres crossing in a tree. They don't come around. They're in a tree. So I tried to draw a tree in 3D. It didn't work. There's not much I can do for transversality in 2D. And here's not a tree where the things are crossing. Okay. So the point is, or at least one branch of research, now we're getting, we were taking huge areas of mathematics that have thousands of people working on it, down to, smaller, a little bit more specialized areas, but still a lot of people working on these things, which is the following question. We know that varieties of rational singularities are nice because we can replace them by their resolutions to do what we need to do with them. And so our question becomes, how can we tell if a variety has rational singularities? And I don't expect anybody to know, oh, actually, this guy, we have the resolution, and we saw that there was one smooth copy. It looked like a circle, but what it actually is the real points of the Riemann sphere. Because we had to remember, let's not go there right now. This guy is much too complicated to be a rational singularity. I happen to know that that's not a rational singularity, that guy. Okay, so here are some results. So it doesn't matter that nobody knows what any of those things mean. It doesn't matter. The point is they're from different areas of mathematics. The first two, Schubert varieties and Richardson varieties, are both sort of from representation theory. Like I said, sometimes varieties come up where you don't necessarily expect to see them as parameter spaces for some class of objects you're interested in studying. These are the cases here, and these Schubert varieties do indeed always have rational singularities, and Mitra Romanoff proved that back in the 80s. 80s? Yeah, 80s. And then Richardson varieties, a related thing, doesn't matter in representation theory. also have rational singularities, and that was proved by two of my colleagues. So that's on the left is Thomas Lamb, and on the right is David Spire, and also Alan Woodson from Cornell. That was much more recent that they showed that. So those are representation theory. Here we have something that I don't know if you might want to call it something close to complex analysis. So the modular space of rank 2 vector bundles on a Riemann surface. That's an algebraic variety and has rational singularities. Makes complex analysts very happy. Because now they can replace the study of that thing by its resolution. Cluster varieties come up in combinatorics, and this is something I recently did with some of my postdocs. So here, Angelica Benito, Greg Muller, he's a roller derby ref, Jenna Reichka, and this is Greg again, so you guys can see his face. I'm me, but I didn't put my picture up because you see me. So these are just examples of different kinds of fields where varieties naturally come up and people are interested to prove that they have rational singularities, and these all do. And what's really amazing about those 4 different classes of varieties that were proven to have rational singularities by different groups of people is that they all use more or less the same strategy, which I personally think is a remarkable and beautiful strategy for studying algebraic geometry. So the strategy is convert the geometric problem about the variety into an algebraic problem about the coordinate ring. Who asked me about the coordinate ring? So that's a very general step about, not all algebraic geometers do that, by the way. That's just more if you're kind of an algebraic geometer or a community of algebraists. So you can convert the geometric problem to an algebraic problem about some ring. And now comes the part that's a more specialized and interesting, to me thing, is then you solve that algebraic problem by reduction to characteristic P. And here I put another mathematical hero. Since this came up, that was convenient. Mel Huxter, who was mentioned, he was my PhD advisor, and he is one of the people, not the only person, who sort of pioneered this technique and really, really developed it. So, yes. So I want to explain that strategy very quickly. I don't expect everybody to follow this, but just reviewing for people who have seen it a little bit. When I have a variety, what I can do is I can take a polynomial function on the space in which it lives, in n variables if I'm in Cn, and I restrict it to the variety. Now I have a function on the variety. It's basically a polynomial function on the variety, but we call it a regular function. If I take the set of all those functions, they form a ring. I can add 2 polynomial functions. I can multiply 2 polynomial functions. So it's a ring. It's called the coordinate ring, and the coordinate ring is denoted as you see here. So here's an example where you see, for the cone, the coordinate ring is this nice quotient ring, because we're in 3 variables, we're in 3 space. It's going to be a quotient of a polynomial ring, 3 variables. And here, for people that want to see it, is the general proof that the coordinate ring is always a quotient. Sorry, the coordinate ring is always a quotient of a polynomial ring in n variables, modulo the ideal functions that vanish on it. It's a really trivial example of Noether's first isomorphism theorem, which everybody knows from algebra. First class algebra. It doesn't matter if you didn't follow all those details. The point is, if I want to study a variety, I can study this ring instead. And what you do in your first course in algebraic geometry is basically understand the black part of this table. So a variety corresponds to the ring, and it turns out in a one-to-one way, the finally generated rings, finally generated C algebras correspond to the varieties, and maps between varieties correspond to maps between the rings. And almost any geometric thing you want to say about your variety has an analog in the ring. So for example, a point on a variety corresponds to a maximal ideal of the ring. It's all the functions that vanish at the point. There's a one-to-one correspondence there. That's a really famous theorem of Hilbert. Hilbert's self-selling stuff. It's usually proved in our first course in algebraic geometry or commutative algebra. And other properties, like whether or not the variety has components or just one component, that corresponds to the ring being a domain. People know what a domain is. So this algebraic condition is this more maybe confusing geometric condition. That's not that confusing. Dimension has an analog called Kroll dimension, length of longest chain of prime ideals. Smoothness has a corresponding algebraic thing called regularity, which actually I lied. You probably wouldn't see this in a first course in commutative algebra or in algebraic geometry. That might come a little later. But it's a basic thing. So you can check your variety smooth by checking this ring is regular, whatever that means, doesn't matter. It's an algebraic thing. You can use algebraic tools on it. So if you like algebra, you can convert the problem in geometry to a question in algebra and then go see if your ring's regular or not. Regular is kind of a generalization of being a polynomial ring. Polynomial rings are regular because they correspond to Cn. That's the variety. Polynomial ring and invariables correspond to Cn. So, like I said, every geometric property you might want to hope for has an algebraic analog, but it doesn't mean that it's easy to find what it is. And the singularities being rational is one of these things that people really cared about, and there's many ways to define it. Some are more analytic, some are more topological, but it still feels like an algebraic geometric condition, so it ought to have a corresponding condition about algebra, and we didn't know what that was for a long time. Now we do. But you can't define it directly. You need to do reduction to characteristic P. So the way we do that, this is just super quick, and I'll say it again later. To study this cone, oh no, this is the second time I'm saying it. To study this cone, for example, we instead study the ring. We already talked about that. And then instead of studying that ring with the complex numbers as the coefficients for your polynomials, we're going to study the rings with Z mod P there instead. So these are a whole family of quotients of polynomial rings, one for each prime number P. And there's infinitely many of them here. And the idea is that if I could prove, for example, that all of these are regular for, say, large P, then it would force this to be regular by some algebraic principle. What do you think? Do you think that these are regular for large P, based on what I just said? Do you remember that regular corresponds to being a smooth variety? This is not a smooth variety. So just by the picture, I know this isn't regular. For any P, it turns out. But anyway, the point is that we can reduce the study of this complex algebraic object, complex geometric object to this algebra over finite field stuff. Studying those rings instead. Why do we want to do that? My analyst friends are like, what are you doing characteristic P? It's crazy. They don't even know what it means, so I review that for you. No joke, I've been married to 2 analysts. I have to tell them what characteristic P means every time. They're good mathematicians. You don't have to know everything. So, P is a prime number, and we say a ring has characteristic P. By the way, all rings have 1. I know your textbook said, maybe you don't say that. All rings have a 1. Our rings definitely have 1. Polynomial ring has a 1. Constant polynomial 1, right? So, we just add 1 plus 1 plus 1 plus 1 and see if we ever get 0. If we get 0 and P is a prime number, we say the characteristic. The number of times we did it is P. We say the characteristic P. That's what it means to be characteristic P. You guys know this, right? You're all really smart. You're studying for the GRE more than 20. So both these rings up here have characteristic 11. Obviously, if I took a quotient of that polynomial ring over Z11, it would also have characteristic 11. So what's the amazing thing about characteristic P? It's what I call the freshman dream. So when you're graduate students and you're teaching, remember, not everybody's as smart as you, but they will discover that it is incredibly useful to use the fact that f plus g to the 7 is the same as f to the 7 plus g to the 7. Students will make this mistake, I promise. And it simplifies their results. Sometimes it proves incredibly powerful things, right? It's very easy to integrate or whatever you want to do, right? It's like easy. It makes things good. Well, this is why we love characteristic P, because it's true in characteristic 7. Well, in characteristic P, if you want to say this. So, in any commutative ring of characteristic P, f plus g to the P is f to the P plus g to the P. Here, f and g are any elements at all. So that's actually a remarkably strong fact, incredibly strong fact. And it's so simple, because all you do is you expand out the binomial coefficients, and you prove a little lemma that says that all of these binomial coefficients are divisible by P, except the first and the last one, which are 1. It's a little lemma, you prove it. So that means if you're in a characteristic P ring, Any integer that's, 1 plus 1 plus 1 plus 1 n times, that's what the integer n means, right? That is going to be 0 if p divides n. So these are all 0 in characteristic p. So the freshman dream is true. So in this ring, any two polynomials, if you want, say, f plus g to the 11, it's going to be f to the 11 plus g to the 11. That can also simplify some computer algebra. That's a really nice thing. Very few terms, keep down the number of terms. So why is it useful? It's hard for me to give you a full explanation other than maybe you made that mistake yourself sometime and you realized it simplified everything a lot. It does simplify everything a lot, and it also gives us extra tools. That extra tool is called the Frobenius map. So you'll hear people talk about the Frobenius map. The Frobenius map is the p power map. So if I have a ring of characteristic p, I always need a commutative ring, then the p power map is a ring homomorphism, and that's basically the definition of ring homomorphism. The first property, that it preserves multiplication, follows because the ring is commutative. The second property is the freshman dream. So the p power map is a ring homomorphism, basically, if and only if that freshman dream holds. So if and only if we're in characteristic p. So like any ring map, you know the image is the subring of the target, right? So this tells me that the set of all p powers is a subring of R. And so I have this like chain of subrings. Like I can do p powers, and then I can apply Frobenius again, and I'll have p squared powers, and these are like the images of the Frobenius map, p power map, just applied forever. It's like a dynamic system. Maybe that's something that's studied that. But even better than that, you remember the first isomorphism theorem again? So when I have a ring map from R onto R to the p, that means that R to the p is going to be isomorphic to R mod the kernel of that map, right? First isomorphism theorem from freshman, not freshman, whenever you take basic algebra, first course in algebra. Isomorphism theorem should be like the centerpiece of the course, usually, I think. And so, as long as you're in, let's say, a domain where if you can't have f to the p is 0 unless f is 0, then that kernel is 0, and that tells us that this is actually an isomorphism. So what we have here is an infinite chain of isomorphic subrings, but they're somehow getting smaller and smaller and smaller and smaller. I think of it as looking in like in a microscope at the ring somehow. And I don't expect you to understand exactly how we use that, because I don't have time to explain it. I need like 3 lectures. But it's not all that complicated. I can try to explain to people who are interested privately. But basically, it's this iteration of this map, this kind of dynamical system, especially using the fact that these are isomorphic subrings, that allows us to use characteristic P to understand singularities. So there's a very long story about that, and I'm just going to reduce it to one simple thing, or one thing that I'm not going to define, but there is a property of rings. So you guys know properties of rings like it's a domain or it's not a domain. That's what I mean by a ring property. It's regular or it's not regular. That's what I mean by a ring property. It's a property that a ring can have. So there's a property that a ring can have called F-regularity. The F stands for Frobenius, and the regularity is referring back to the regularity, which corresponds to smooth varieties. And there is a property of rings called F-regularity, which these two guys, Mel Hochster and Craig Hudicke, define and use to prove all kinds of stuff in commutative algebra, not really algebraic geometry directly, commutative algebra, using the fact that if I have an F-regular ring, basically I can operate Frobenius as if the ring is actually regular. So that's kind of what F-regular means. So what it means is I can kind of assume that the ring is really nice if I'm F-regular. Nicer than I ought to be able to. And that has to do with understanding that chain of subrings in a simple way. So later, these guys are not particularly algebraic geometers, and like I said, these are commutative algebraics. Commutative algebraics are kind of a type of algebraic geometry. But I was always interested in geometry, so I tried to understand what this is geometrically. What is the property of a coordinate ring that if it's F regular, I know the variety has some nice property? Right? Because remember, there's this dictionary between algebra and geometry. And this F regularity property, as it turns out, is the thing that corresponds to rational singularities. I'm oversimplifying and lying a bit. This statement that's here is basically true, modulo the imprecision. It's pretty precise. At least if my variety is defined by integers, I'm basically precise. So if I have, for example, let's go back to the cone, because this cone, what we're saying is it will have rational singularities if all of these rings for large P are F regular, this thing that Craig Minkey and Raj defined. And it does. These rings are F regular, and this ring does have rational singularities, which is good because we verified that by looking at the resolution as well. But the good thing about this theorem is, believe it or not, I mean, my analyst friends never believe me, but believe it or not, it is practical. You can check this. You can actually check this thing. And that's how those 4 different theorems about varieties with rational theorems are all, actually not all of them, some of them predated this theorem as stated, but some of the underlying techniques were also involved there. But at least several of them up there were directly, basically corollaries of this. And this is used to prove things have rational singularities pretty regularly. It's a pretty applicable thing. It's practical to check this condition. Okay, so, maybe I should say more about these people. And Mel, again, I had his picture before. He was my PhD advisor, and Craig Minkey is my other postdoc advisor because I was at Purdue and MIT, various points. So that we're just honoring them, and also they defined F regularity. Okay. On the other hand, I love Mel, but he told me not to work on this problem. He had no idea how to do it. Don't always believe your advisors. Don't always believe. Okay. So just, putting words up there, but also the interesting part is the people who did these things as well. These kind of ideas have been used in many different contexts to study related singularities of complex varieties or properties, objects that come up in complex geometry by converting it to the ring and then reducing mod P and then understanding all these things. And here I put in a plug for my friend's graduate programs. Well, Richard McStott is actually my program. So he's one of the people that worked on some of these things. He's one of my collaborators. He's a professor at Michigan. Carl here is a former postdoc of mine who's now at Utah. He's had several graduate students already. And Kevin Tucker here, his first student just graduated from UIC. He's a professor at UIC now. And she's coming to Michigan for a postdoc. So these are some of the people involved with these things. Okay, I have two more minutes to describe a numerical measure of singularities. Remember we talked about it would be nice if we could put a numerical measure on how bad the singularity is. That would be a nice thing to do. So there's this thing called the F-pure threshold. I'm not going to define it. I'm not finding much here right now. But the big picture idea is that this is a number we give to a polynomial of characteristic P. So here, this polynomial, y squared minus x cubed, its F-pure threshold depends on the characteristic. And here I wrote down the formula so you can see it. And what I want you to notice, which is a remarkable thing, it depends on the characteristic, and these kind of computations are difficult. This one is well known. These are difficult in general. But what you see is that as P goes to infinity, remember how I said you can kind of think of the complex thing as being given by the family of all the characteristic P things? As P is going to infinity, these numbers are converging to 5, 6. And 5, 6 is a magical number for this curve because that's what analysts call the analytic index of singularities, or the law canonical threshold is what some other groups of people call it. A lot of different names for things in math. You can define that as where integral converges. So this is an interesting example, and it leads to this theorem by, I ran out of space to put their pictures up. These guys are some friends and collaborators of mine in Japan, and they proved that this limit always exists, basically, and that it always converges to this number that comes up in analysis. That's an amazing thing. There's this really deep interplay between the algebra and the geometry, and even the analysis, because this number is really kind of defined as an integral, some number you get from integration. So I just have one more slide because I want to show you cool pictures. That F-pure threshold is incredibly difficult to compute, but it's incredibly interesting. These pictures are work of Daniel Hernandez here. He is a professor, assistant professor now at Kansas, former grad student of mine, and he is probably the best expert in the country on computing the F-pure threshold. And with his collaborator, Teixeira, they've been computing all kinds of interesting examples. And I just wanted to show you, this is just like a diagram that shows what the F-pure threshold is for some certain family of curves, and in different characteristics, characteristic 2, characteristic 3, characteristic 5. And what you see is kind of interesting because you can see it kind of converging. You see that? So if you did p equals 7, you get like another, what is that thing called? You guys know. It's a Sierpinski triangle or something? Except this is a Sierpinski triangle. This is some 5 version, and there's a 7 version, and so forth. Anyway, it converges to just a nice, polygonal thing, which corresponds to not the F-pure threshold, but this analytic index of the corresponding family. So it's super interesting work. It's very computational and interesting. And Daniel has run some RUs. I don't think he has to do it this summer. So, yeah, these are all good people to work with if you're interested in any of these topics. Thanks. Yes.
You mentioned a lot that if there's like a singularity, you can like fix or resolve it.
Yes.
Does it go the other way? Like if you have a smooth variety that it always has, it's not a resolution.
Oh, that's an interesting question. If you have a general variety, is it always a resolution of a smooth variety? I think the answer is no. And that's a good question because that's the kind of thing people study related to the idea of when do we have the best resolution? So the question is if we have a resolution, how can we tell it kind of has some extraneous stuff? I didn't talk about how Pierre got these resolutions, but what he does is a process where he finds an algorithm for the resolution where you first identify the most singular part of the variety, and then you do something called blowing up to that, which is a kind of surgery that gives you a better approximation that's less singular in some way. You find the worst singular thing of that, and you blow up it again, and you keep going. And you have to keep going until you get something smooth. It proves it eventually stops. But then you could keep going further and keep blowing up smooth things, and you would have another resolution that would be a minimal resolution. So what you're kind of asking is, yeah, it's a good question. I think the answer is no, though. But you could probably adapt it to be actually a very interesting question. Go ahead.
Maybe a little bit of a stupid question, but does the F-pure threshold exist for any eligible case, or can it just not exist in some cases?
It exists for every polynomial, over any field of characteristic P.
Okay.
Yeah, it's a thing that you can define for any polynomial.
So most of them are just trivial.
No.
Or uninteresting.
No. Most of them are really hard to compute. We don't know them. Actually, let me go back a slide. If you have a polynomial which is defined as a smooth variety, the F-pure threshold will always be 1. But if the variety is not smooth, it will always be smaller than 1. Positive number, smaller than 1. It's actually always rational, which is obvious. I haven't defined it, so of course it's not obvious. So it's a rational number. Yeah, they always exist. What's not obvious is that the limit always exists. That's not obvious. I mean, that's true. That's a theorem. Yes.
For the resolution, can you always do it with as many or fewer variables?
No. Typically, when you resolve the singularities of a variety, the resolution, the smooth variety that maps to your singular thing, will be embedded in a much larger ambient space. So in the examples I gave, I was, for the purpose of being able to show you a picture, I was forced to choose extremely special cases where the resolution also lives in 3 space in this case, right? Because we can't see, if I started with a variety in 2 space, I mean, you know, a 2-dimensional variety in 3 space is about the most complicated thing I can draw and show you on a picture. Does that answer your question? Yeah, typically it's going to be in many, many more variables, but it's not going to be defined by one equation. There's going to be many equations. Yes?
Is there an upper bound for how big the space resolution is?
That is an excellent question. I worked on that when I was a young and foolish mathematician and never found the answer. I mean, there's no upper bound in general, but you can ask, if you have a variety defined by one polynomial of degree equals d, is there then an upper bound? And I think in that case what I just said probably is yes, and I can find it. But like that kind of a question, there's not a general answer that I know of, and I think it's pretty hard. I mean, it's not a bad question though. It's related to, oops, question 2 here. What is the smallest dimensional space into which the variety bends? So you're kind of asking the smallest dimensional space into which the resolution bends. It's an excellent question. People are very interested in varieties in n space of dimension d that can be defined by exactly n minus d equations. That's kind of the nicest thing you can hope. Like a hypersurface defined by one equation, for example. And they're not always going to have. I don't think they always have that property. I don't know, actually. Good question. Yes?
Do these characteristics, P characteristics of your results use model theory at all?
Model theory. No, but model theorists have looked at these things and have their own way of thinking about it and describing it and understanding it that I don't fully understand and reproving some of our results. I don't think anything specifically I have up here has been specifically reproved by a model theorist, but there are other things. Yes. So the answer is yes, this is closely related to model theory. Like I said, there's lots of different camps of mathematicians that have their own language and own techniques. And you know, math is extremely complicated, but also it's not that complicated when you really, really understand it. And, you know, stuff kind of comes together as we get a bigger and bigger picture. So yeah, model theory is definitely closely related to studying varieties by direction curves.
Anybody else?
Yes.
What can we say about the singularities of a homogeneous hypersurface? So it's in some degree a number of variables, but and every term has the same degrees of homogeneous.
Yes. One thing you can say is if the variety has, so first of all, it's going to have a cone-like shape to it. Have you thought about that?
Well, I'm not, with this highest degree, it's very difficult to visualize it.
What I mean by cone-like shape, so you have 7 variables, is that what you said?
Maybe 70 variables in degree 10.
Okay, so it's 7 variables in degree 10. So what I mean by cone-like shape is if I take the origin and I take a point on the variety, I take the line connecting the origin and that point. You picture a point in 70? I mean a line in 70?
Sure.
Yeah, sure. It lies on your variety. It's kind of any zeros of a homogeneous polynomial is kind of like a bunch of lines tied together. Like we saw that here, actually. See, this is a bunch of lines tied together.
Right.
It'll always have that kind of cone-like shape to it. So if it also has an isolated singularity, if there's only one singular point on it, it will necessarily be the cone point when they come together like that. And then I know how to resolve the singularities. All I have to do is blow up that cone point. Whatever that means. It's a kind of surgery. Actually not that hard to explain. Way over time, so I don't do it. Yeah, so yeah, those I do understand pretty well. And because we can understand those pretty well, that's why you'll see lots and lots of research happening. You know, why do you guys work on what you work on? It's usually because you can, right? So we can study homogeneous polynomials, and we can look at their zero sets much better than we can fully arbitrary polynomials. So yes, it's a very active area of research. I can tell you exactly the formula for the rational singularities in terms of the number variable. If it has an estimate.
Okay, so I guess we can continue our discussions over dinner.
Sure.
It's going to be upstairs, right? In the math hour, 7 o'clock. Okay.
Is it starting now? 6:30. Okay, so I can tell you privately.
Okay.
talking about writers math and like seeing there and like this.
When I define sobriety, like you're going to feel comfortable. Yeah. Because I actually don't care if I you know, I'll just yeah. So really, I'm talking about Steve. Yeah. Let it understand. And also, especially Chicago, 1% of what you're studying when you're here.
That's
It's actually extremely small. You'll confuse.
That's a very
I know. I'm the graduate director of the so I have to listen. They've always taken it on. Yeah, it doesn't matter. So we're doing varieties of C.
It's like groups of people.
Or does it matter?
And that's why the question of like characteristic stakeholders
Correct. Correct. CP is not a real.
This proposal has been being recorded.
Yeah, I don't know.
Like,
We should stop it.
yeah, we should stop it
But how?
here. I hope we don't erase it. Recording in progress. One wording. The control panel is looking to record an area of recording. Finish.